Okay, in the lab we looked at position and time and how those two variables were related. So you had the dune buggy, it was moving, and you either picked which times you wanted to record the position at, or you picked what positions you would record the time for. And that again tells us which one was your independent variable, which would be on the x-axis, or your dependent variable, which would be on the y-axis. Depending upon those, we're going to assume that this is the same exact dune buggy, but performed in two different ways with a different independent variable each time. If I chose time as my independent variable, my slope turned out to be, for this particular example, 0.5 meters over seconds. And then if I did it in the other way, or the other fashion, with position as my independent variable, the slope was 2 seconds over meters. With that being said, we can write equations for these. We have a straight line, so we can write an equation. We have a slope, and we actually do have an intercept on both of them as well. So if you look here, I have an intercept of 1 and an intercept of 4. So we'll talk a little bit about in these boxes below what that means through words, because sometimes when we just state numbers and units, we lose the actual meaning. So the slope for this first one, the position versus time graph, is telling me that the buggy travels 0.5 meters for every 1 second that passes. Or in general, you kind of hear things like, I'm going 30 miles per hour, or mph as we say it, but really that means miles over hours. For the other example, or the other way of doing the lab with position as our independent variable, our slope still means something, but it's just not in terms of how we talk about driving. So this one says, the buggy needs 2 seconds to travel a distance of 1 meter. This is in comparison to saying something like, it will take me 15 minutes to get home, which is 6 miles away. So something like that. It's going to take me a certain time, and we imply a certain distance by the saying home. I don't think many people talk like, oh, it's going to take me 20 minutes to travel 3 miles. So again, we use it as a locational thing. All right, for what this actually means, which we talked about in class, the slope on this position time graph, so the slope on the position time graph, the one right here, means velocity. And the slope for the time versus position graph, we don't have a word. Nothing in our language that we use to describe saying, it will take me 15 minutes to get this distance. Talking about the y-intercept for each of them. This is kind of just at time 0, the position is, and then whatever we have, it actually happens to be 1 meter there, but at time 0, the position is this. So that's telling me that I started at a point other than my origin. The term we use for that is initial position. So what's my initial position, my starting point? On the other graph, or the other way that you could have done the experiment, this is called kind of, again, still the y-intercept, but it's at a position of 0. The time is And in this case, it was 4 seconds. Not really the most meaningful thing in how we speak, but if you really wanted to look at it, that is the initial time. All right, and as we can do with any linear relationship or linear graph, we could write an equation to describe what we're looking at. So for this one, instead of y, which is where y equals mx plus b format, my y is not really y, it's actually specifically position. So position is equal to the slope, which I'm going to write the actual slope for this one here, 0.5 meters for every second, times, so that's my y and my slope, times, x is not really x, that does not mean position, it's talking about your x-axis, your horizontal axis. So times time, a lowercase t, plus, and then we had an initial position of that point at 1 meter. So I'm going to include that in there. We generally like to put things in the most generic terms because then we can apply it to other scenarios. So not everything that has this kind of motion or that constant pace is going to have that velocity of 0.5 meters per second. So we can simplify this down, and I'm going to use variables. So instead of position, I'll write x. Instead of my slope is velocity, so I will write v, t for time, and then my initial position, it's another position, but to signify that it's an initial position, I use a subscript I. And the position over on the other side is really considered to be the position at any time you're talking about, but the final position at that time. So we can call it x sub f. This is an equation you can use for anything that is traveling at a constant velocity. We can try this on the other side. We would have, instead of y, it's now time on our y-axis. And instead of our slope, we now had 2 seconds for every meter. Instead of x, we have position. So, yay, that gets to be x again when we write it out. And then plus our intercept, which was 4 seconds. If I wrote that in abbreviations, time is equal to, no word, shoot, so we just have to leave it blank, times x plus your initial time. So, since there's really no word for that, we don't use this equation. You could call it the inverse of velocity, but why would you? We would just want to use this one. Okay. For that, we can come down here and reiterate a little bit of what we talked about before with the terms of velocity and speed. We know we had velocity from our graph, so velocity is abbreviated by the letter V, units of meters for every second. And an operational definition is the slope on a position time graph. So the slope of this one. And in our definitional term, it's kind of how fast something is moving and in which direction. So we have to relay not only the speed that we're talking about, but also the direction. If you want an equation as a definition for velocity, we can look above at our equation over here and solve for V. So if I use that xf, or x final, position final is equal to velocity times time plus xi. To solve for V, making it an equation definition, I can subtract over initial position, so that gets me final position minus initial position equals V times t. In other classes, you usually abbreviate this xf minus xi with a delta x, talking about the change in position. So I'm just going to throw in the delta to signify the final minus initial. You've probably done that with temperature before. That's equal to velocity times time. Still, we want to get velocity by itself, so divide both sides by t, and you're left with delta x over time equals velocity. So we have that equation, an operational definition, and some words for our definition here. We'll talk a little bit about delta x in a bit. The term that you're probably used to using or interchanging with this is speed. And speed, we use S to abbreviate for. It's still in meters for every second for units, but this one is just simply how fast something travels. There's no direction. Therefore, not the same thing as velocity. I'm going to go to the back side, and then we'll come back and reevaluate these two with a little bit more of a detail. So on the back side, you have a couple questions. It's asking, or it tells you, an overhead snapshot of Dorothy and Toto walking along the yellow brick road is shown below. Toto is the dashed line, Dorothy is the solid line. And then it asks two questions from start to finish: who travels farther? Justify your answer, and develop two different definitions for measuring how far something travels. So if you want to do this on your own, go ahead and hit pause and then come back to listen to what we should talk about. Okay. From that, really this is just a bad question, because farther, it's not descriptive enough. It could be really one of two things. You could say that Dorothy travels farther because she traveled from here to here. So she ends at a further distance away from where she started. Or, and especially compared to Toto, because Toto just traveled his starting position and final position. That's the only change he had. So he technically started off and a little bit ahead and ended a little bit earlier, therefore making the total distance away from his starting point and ending point smaller than hers. But if you look at Toto and you say, hang on a second, Toto didn't just travel from those two positions. Toto actually traveled along this whole line. And if you were to take that line and straighten it out, or stretch it out so it was straight, that line would be much longer than Dorothy's. So, what's the right answer? Again, there's really no right answer for that. It's just the fact that we need to have a better definition. So if I'm talking about the actual stretched out line from Toto, if I were to just straighten that out and measure that, that is considered something we call distance. If I were to look at just the change in Toto's position from his start to his end, that is called displacement. So we have two different terms here, distance and displacement. Again, sometimes they're the same, but they are not always the same. In Dorothy's case, her distance and displacement are the same. In Toto's case, displacement and distance are both different for him. So those were kind of our two definitions. We can go back and look at our important terms. So if you want to just review, this is called, we would have position, abbreviated by X. That is officially where an object is located with respect to something, usually the origin. xi or x sub I is initial position, and xf is final position. The next term we have was distance, abbreviated by the letter d, lowercase d. This one is how far an object travels during a specific time interval. It's also kind of considered the absolute value. If you have, it's always not, it's not taking into consideration direction. So if you go backwards, you're still counting it. This is something like what path you took. Or if you were to use a Fitbit or an odometer. Those are very route dependent. And the lights. That's always awkward. All right, the one below that we'll save for displacement, abbreviated by delta x. This stands for the change in position, or kind of well defined as how far and in which direction an object moves in a specific time interval. And I said delta x because, again, delta x is the same thing as saying final minus initial position. So that's kind of what it's telling us. As far as direction, we will use some different conventions to talk about direction. You could either have a negative direction or a positive direction. Those are the best convention we can kind of come up with. Negative and positive can be talked about as forward and backwards, or up and down, left and right. They kind of have that negative or positive associated with it to tell you that it's the opposite of the other one, just like we use negative and positive in math. The last one we had down there is time, abbreviated with a lowercase t, measured in seconds. This is kind of not the best definition, but how much time has passed, or the change in time, or sometimes talked about as time interval. Technically, it's really delta t, but most people just kind of don't write the delta down, so we'll kind of get used to that as well. The two terms we also talked about were those general terms that describe quantities. So we have either a scalar or a vector. A vector is defined as a quantity, and in our case we usually are talking about measurements, with both direction and magnitude. Magnitude means size. So if I was talking about the magnitude of my height, the magnitude of my height would be the number, the numerical value, so 5, 6. My height doesn't really have a direction. We could kind of say up, but not really. It's just a relative distance. So magnitude, again, is just the numerical value. Direction is, again, specifically talking about which way. So you can think of your cardinal directions, north, east, south, west, or our convention that we will be using will be that up, down, or left, right. Up's going to be positive, down's going to be negative. Left is going to be negative, right is going to be positive. West and south will be negative, north and east will be positive. So those are directions that we would include. So anytime you have a value that has a negative or a positive sign, that's giving you something about the direction that it's moving in. The scalar, more probably common in what we've been talking about in the past years of science, when you're measuring mass or something like that, you're just measuring a magnitude. So this is a quantity. And again, in our case, we talk more about measurements with just magnitude. And again, magnitude means like the size or amount or the quantity, which I already said, or the number. Really, it's the number that you're looking at. Going back, these are general terms. We can look at our variables that we've had for so far for this unit and decide whether or not they are a vector or a scalar. Time, some people, just have large debates about what time really is. It is a scalar, or is it a vector? Can time go forward or can time go backwards? Does it have a direction? So I'm going to leave that one to the coffee shop arguments that people have when they talk about vector versus scalar for time. But going to displacement, if I have a change in position, it most definitely is going to matter which way or which number each one of these was. I could end up with a negative displacement if I have a greater value as my initial position and a smaller value as my final position, which again, it's based on an origin that you set, but then that definitely is a vector. Distance has nothing to do with which direction. It's path dependent, so no matter what direction, you're still counting it just the same. So that is a scalar. And position, again, you could really talk about position being relative to that, something like the origin. You could have a negative position or a positive position. So I tend to go with the fact that that is a vector. Going back to the front of that, velocity, because it has a magnitude, so how fast and in which direction, velocity is definitely a vector. Speed, no direction, it's just how fast something is traveling. So speed is a scalar. All right, after going through this sheet, you should really have down the terms, the differences between velocity and speed, the difference between displacement and distance. To bring back the idea of these terms and how they're important, notice we have delta x in the equation for velocity. So if I really wanted to write this out, I could write velocity is equal to displacement over time. Realize displacement's a vector. Whenever you have a vector somewhere, it's going to cause another vector. If this displacement had a direction, the velocity has to have a direction. For speed, this is an equation we derived, but it's something that you've probably learned in the past. Speed is equal to distance over time. The difference here again, distance is not a vector, it's a scalar. So no vectors over here, speed still ends up being a scalar. So scalar, scalar, scalar. When I look at these two equations, I see the difference is really in displacement and distance, therefore causing velocity and speed to be the answer. All right, we will work more on this and using position time graphs to talk about velocities and kind of looking at where displacement falls in with that as well. Have a great day.